Let me also share my screen. Okay, are you able to see my screen?
Yes, I can see your screen.
Okay. So I welcome you for the week 11 interactive session for the course Polymers Concepts, Properties, Uses and Sustainability. Okay, now as usual, let's go through the recap of week 11 lectures. So week 11 lectures was also on the polymer processing and recycling technique, where rheology was a major focus of this week. Okay, so lecture 78 was on rheology and entanglement. It was based on concepts. So, rheology, which is a study of deformation behavior of fluids. So here the discussion was on shear flow, extensional flow, and then where, how using the rheometers you can make the flow as one dimensional with narrow gaps and control many variables, so that you can understand the flow behavior elaborately. Okay. uh, uh, in fact, in polymer processing you will have uh, you know large deformation and non-linear rheology, where we have studied during the viscoelastic behavior discussion. We studied on small deformation and mostly covered on the linear rheology. But in actual polymer processing, you will have large deformation and non-linear rheology. So non-linear rheology becomes a critical factor in polymer processing. And in understanding the material behavior for subjected to large deformation. Okay. So rheometer geometries, especially for a rotational rheometer, was discussed. And these rheometers, the geometries are of thin gap. The gap between the geometry is, whether it is a Conan plate or a parallel plate or concentric cylinder, is very small. Okay. And then how is the oscillatory shear response of a polymer melt, were all discussed. And then how the extensional flow in case of a branched polymer, it differs. How the strain hardening, it significantly differs in case of a linear and branched polymer. And when you find in case of a linear polymer, the strain hardening is very less, whereas when you go in for a branched polymer like LDP and all, no, you will find a significant strain hardening, which extensively helps in easier processing of these materials. Okay. And then fiber orientation, how the fiber orients in a shear flow and extensional flow, were all discussed in the lecture 78. Okay. And then lecture 79. One second. You're able to hear me, right? Yeah. Yeah.
You,
Yeah.
I can
Lecture
hear.
79 was on rheological models. So different classes of models, like linear viscous models, non-linear viscous models, which is nothing but your generalized Newtonian fluid model, uh, uh, were discussed. And then linear viscoelastic fluid, how, what is the model. And then this was followed by shear thinning models. And shear thinning models, two major models are Karayu Yasuda model and Herschel Bulkley model, were all discussed. And this was followed by a small introduction on the non-linear viscoelastic model, which is a one of such model is Pantheon Tanner model, PTT model. Okay. Here you have convected derivatives. Okay. And you make such that you would have gone through in your fluid mechanics, your Lagrangian and Eulerian frames and all, where in Lagrangian frame you move with the sample. So a concept very similar to that. Here also you make the frame indifferent, and it is more on the material objectivity. So these concepts were discussed in the rheological models. Okay. This was followed by lecture 80, which was on rheology and processing. So in rheology and processing, this was on uses. So how is the mixing in different flows, and what happens in case of polymer mixing. So polymer mixing is basically involves laminar flow due to the viscosity. Okay. And what happens in case of a simple shear flow, where the a point of separation between materials is linear in nature, whereas in case of exponential flow, the point of separation in extensional flow, the point of separation between two materials is exponential in nature. And then viscous dissipation was discussed, and dye or extruded swell. So this dye or extruded swell, so when you pass the polymer through a dye, the product that is getting extruded or coming out from the dye may not have the same dimensions as that of the dye dimension. This is due to when it passes through the dye, there might be stretching and orientation, and once it comes out of the dye, so due to the viscoelastic nature, there will be a recovery, which are due to the entanglements and reptations. So this causes a dye swell or a extrudate swell. And you know this has a correlation and influence of the normal stresses as well. Though it might be only a shear flow, but there is a significant influence of the normal stresses as well. And then this also has influence of interfacial properties as well. Okay, so these concepts were discussed in the lecture 80. And further, what are the deformation in simple shear flow, and velocity gradient, strain rate tensors, stress rate tensors, what are the components of each of these, and what are the expressions for a Newtonian and generalized Newtonian fluid were all discussed. And in case of a stress tensor, in how it differs in case of a simple shear flow, and for a viscous fluid and a viscoelastic fluid was also discussed. Like the total stress tensor, the deviatoric stress tensor, where in case of the deviatoric stress tensor, the normal component also plays a role in case of viscoelastic fluid, and the normal stress difference were all discussed. And different techniques of rheology, like rotational rheometry, tube flows, extensional rheometry, and trade test were all covered in this lecture. So this was followed by lecture on absorption and leaching, which is based on the concept of sustainability. Because obviously the polymer waste are sometimes thrown in water, okay, or in soil, or it comes in contact with air. So how does material, small molecules may get inside the polymer and also get leached out of the polymer, which plays a significant role in environmental impact. So the fate and transport of polymer in environment, especially because of their low density and long life of polymers, since the biodegradability is of course very less in case of polymers. And how the exchange of small molecules, for example, a small molecule getting absorbed by the polymer and getting leached out of the polymer, both play significant role. And thermodynamics of solute exchange, like solubility, partitioning, and sorption isotherm, kinetics of solute exchange, these all plays significant role, especially in absorption, leaching, or for polymers. And absorption kinetics, different kind of kinetics it follows, like Fickian, non-Fickian, case 2 diffusion, and were discussed. This was followed by leaching and leaching kinetics. And the next lecture was on swelling of polymers. So spelling, what is the spelling of cross-linked polymers, and what is the interaction when a polymer is linear or branched. So solvent polymer interaction, in case of just non cross-linked polymer, it may get plasticized, followed by solubilization, and forming a polymer solution. Whereas in case of a cross-linked polymer, what happens is that it doesn't solubilize, but it starts swelling. And what is the relationship of osmotic pressure and chain elasticity in case of swelling were discussed. And how this swelling, it is very useful in different applications, like in case of super absorbent material. And how does it help in measuring cross-link density, and how does it play a role in hydrogels and organogels? Okay, so for example, this may be helpful in drug delivery and all. Okay, and flow reagents theory and network elasticity, where swelling ratio based on the weight and volume was discussed. And this was followed by osmotic pressure. How does it change in Gibbs free energy the solvent starts traveling in, and what role it plays, and how does the network elasticity, entropy based, all these, it plays a role in swelling ratio and all were discussed. And a discussion on the Flory-Rayner equation, which is a force balance equation between the osmotic pressure and the network elasticity. Okay, and kinetics of swelling. So what are the components, like mass transfer, it affects the kinetics of swelling, and then large deformation, relaxation processes. Okay, these things were discussed in lecture 82. And the final lecture of the week was on viscosity for polymer processing. Hello, are you there?
Yes, yes, of course.
So
I'm
you're
here.
able to follow what I'm.
Yes, yes.
Okay, did you go through the lectures?
Not really.
Okay, so this will just give some idea on what are the concepts that
Yes,
has been discussed.
yes, yes, yes.
So the final lecture of the week was on viscosity for polymer processing. So where capillary rheometry was discussed, and for example, Newtonian fluid. So capillary rheometry, obviously it involves the pressure difference. Okay, for any material to pass through the capillary, you need some pressure difference. So in case of a Newtonian fluid, you have the Hagen-Poiseuille equation, where there is a relationship between the pressure difference, and you will have the viscosity term as well. Whereas in case of viscoelastic fluid, you cannot use a Hagen-Poiseuille equation. Whereas the equation of motion itself, from the equation of motion, you can develop the relationship between the shear stress of polymer and the wall. From where you could find out the viscosity of the polymer in capillary geometry. And you know uh, the developing flow and entrance effect, you will have some end correction in case of the equation. So one of such correction factor is called as Bagley correction factor. And Maxwell model in terms of viscosity. So in earlier classes, during the discussion of viscoelastic models, the Maxwell model was discussed based on the sinusoidal strain input. And the model was expressed based on your modulus, your storage modulus and loss modulus. Right? Do you remember G prime and G double prime? Hello?
Yes, yes.
Yeah. But in this, based on the viscosity for a viscoelastic fluid, so the input is a sinusoidal strain rate, and the model response was based on the viscosity. Okay, where you had eta prime and eta double prime. So these are the concepts that were covered in week 11 lecture. Okay, now let's go on to the practice assignment. Okay, the first question: in a Conan plate viscometer, the rate of strain is related to the speed of rotation of the cone, omega, and the angle between the cone and the plate, alpha, by following relation. Is it related by the relation that the strain rate is equal to omega into alpha, or strain rate is equal to omega into cos alpha, or is it uh, alpha by omega, or is it omega by alpha? What is the relation? This was a gate question asked in gate 2013. You have any clue on this?
Viscometer. Normally,
अच्छा अच्छा हाँ तो 10-15 मिनट लग
radial
रहे हैं
per
बनाने
second
में
and alpha is the radial
हाँ
by following relation. Alpha it should be radian per second. It should be alpha upon omega.
You mean to say, is it option C or D?
C.
C, you're saying.
Yes.
The correct answer is, it's
D.
actually
Okay. Reverse.
omega.
Yes.
So
Yes.
rotation, I mean the speed of rotation with this one,
Yes.
your alpha. So
Yes.
you
Yes.
can
Yes.
actually easily
Exactly.
find it out, because the unit of strain rate is nothing but second inverse, right?
Right.
So radian per second by radian. So obviously you will
Right.
end up with second inverse.
Right.
Okay.
Right. Okay.
Yeah. So one of the key feature of rheometry is narrow or thin gap. So what is, this narrow or thin gap does? So what does it make to use a thin gap, so that something is made as insignificant? So when I was discussing the recap, I was saying that the rheometers in the rheometry, they use thin gaps, like whether it is a Conan plate or parallel plate, right?
Yes. Yes.
So why are they using the thin gap? To
Thin gap is very mandatory actually for any rheometry, so that we can check the resistance of flow. If there is a wide gap, so we cannot observe or we cannot measure the resistance.
Why can't we measure resistance? Anyway, the flow is going to be there. You will be accounting, the flow will be, kind of a shear flow. So
Yes.
you can measure the, anyway you have the, formula for the, which includes the height and everything. So the flow, it goes in the y direction. So you can obviously, you can find out the resistance, or your viscosity, whatever it is. But what makes, you know a thin gap a mandate, or why is it a key feature? There is something beyond.
Maybe non turbulent flow.
Not turbulent flow. No, you can make a laminar flow. Of course, a flow through a pipe, when you go through the fluid mechanics
Hmm.
class also, no, flow through a pipe, you can make it, laminar. In fact, in your
Okay.
polymer processing, the flow is laminar, right?
Hmm.
The flow and mixing all are laminar because of the viscosity involved, right? There
Right.
you are
Right.
not going to have any thin gap. So
Mhm.
what is it that?
No idea then.
Okay. It is actually your inertial, you're eliminating your inertial forces. The impact of inertial forces is eliminated, because as you
Okay.
increase the gap due to the, rotational flow, this is the rotational rheometry, especially in rotational rheometry. So as it rotates, if there are high inertial forces, then it would affect your data. Not only that, this sample might be thrown out. Okay, as you make the gaps thinner and thinner, you will not have this inertial force impact. That is one of the key reasons to have thin gap. Okay. Hello.
Yes. Yes.
Yeah.
Okay.
Okay, fine. You got it. Okay. Perfect fiber orientation can be achieved in which flow? Let me give you a clue, whether it is a shear flow or an extensional flow, which will help in alignment of perfect fiber.
Maybe non extension flow.
Extensional flow, you're saying.
Yes.
Why do you say so?
See, in shear force, whenever you are applying shear, so there is a lot of turbulence over there. So the orientation cannot be perfect, cannot be aligned in proper way.
I said because of the turbulence.
Yes.
But does turbulence really play a role in case of a polymer processing, especially polymer composite processing?
Not in processing, but of course in orientation.
No. Do we really have turbulence in polymer processing? There is no
No.
question of turbulence at all, right?
Yes.
So the actual reason is that it,
Mm.
as you said, it is due to extensional flow. So
Yes.
extensional flow, obviously, you will have in a single axis, right?
Yes.
So it will be more of a uniaxial flow. So what
Yes.
happens is that the fiber starts aligning in that particular axis, whereas in shear flow it is a layer by layer flow.
Yes.
So
That's
there
right.
the effective orientation might not be there for the
Yes.
fiber. So extension, that is the reason why extensional flow, you know,
Yes.
it helps in better fiber orientation in case of polymer composites. Okay.
Right.
Yeah. Okay. Now let's go on to question number 4. Match the following rheometry geometries with its features or application. So Conan plate geometry, concentric cylinders, parallel plate geometry. So, and the features or the application are low viscosity samples, and non-uniform strain rates, uniform strain rates, and suitable for paste like systems.
So concentric cylinders is basically for low viscosity. That is for sure.
Okay.
And then cone and plate geometry is for maybe paste-like systems,
So
or
for
maybe
paste like
four.
systems.
Yes. So basically high viscosity systems. So as I can correlate, like A is for 4 and B is for concentric cylinder is for low viscosity, means B is 1, and parallel plate is basically for uniform strain rates. Yes, 3.
Is it so?
Yeah.
Okay. Let me say one more thing, that one of the uh, geometry,
Mhm.
it matches with two of the features or application. That
Okay.
is okay.
Okay.
And one of your answers is right.
Yes. So concentric, I'm 100% sure because we are using concentric cylinders
Okay, okay,
for
you're
for
right.
our because our ink are the low viscosity materials.
Okay,
So
okay.
we
So,
are using concentric cylinders for low viscosity materials.
okay,
Even we can see the for water flow meters we have concentric cylinders.
okay, okay. So you're right in that. So what
Yes.
about the parallel plate and Conan plate geometry?
Uh, Parallel plate, maybe in my view it should be for non-uniform strain rates. We can use parallel plates.
But earlier you told for uniform strain rates.
Uh, no, uniform strain rates, and for high viscosity we can use cone and plate geometry.
Okay, you're saying 3 and 4 are for A.
Yes.
Okay, okay. So shall I reveal the answer?
Yes, please.
You're partly correct, partly wrong. So,
Okay.
cone and plate geometry, as you said, it is for uniform strain rates. Okay.
Right.
Here,
Yes.
because since you have a tapered cone end, there always, the center viscous, the velocity will be high, but as you go through as you go along the radius, your your velocity increases,
Yes.
and simultaneously your height is also increasing, so your strain rate remains uniform. Okay.
Oh, okay.
Whereas in case of parallel plates, as you said, since it is parallel, again, your velocity will increase along the radius, but the height is not increasing, so your
Yes.
strain rates are not uniform.
Yes.
But there's one more thing, is that in case of cone and plate geometry, what happens is that since you have the tapered cone as a geometry, I mean the top plate is conical in shape.
Hmm.
Okay. So the height, the gap between the platens, okay, it is restricted, okay, to less than zero point 0.5 micrometer, sorry,
Okay.
for less than 0.5 mm.
Hmm.
Okay. So here if you use space like systems, there is a probability that it will get thrown out, whereas in case of a parallel plate, you can adjust your gap, like from 0.5 mm to 1 mm. So in
Yes.
that case it is more suitable for a paste like systems.
Yes. That's right.
Okay. So this is
Yes.
the logic. So parallel plate is for non-uniform strain rates, and it is also suitable for paste like systems. Okay.
Yes. Okay.
Yeah.
Got it.
Now let's go on to question number 5. According to Caruso model, constant viscosity at low shear rates is called
constant viscosity at low shear rate is called uh, maybe
So
it is a phenomenon of like non-thixotropy. I do not know what word we are going to use here, but we are
see,
using
this Carrier-Vesuta model is for shear thinning fluids. Okay.
okay.
So shear thinning polymers. Okay. So
Hmm.
what happens at very low shear rates?
Hmm.
Your shear
Got it.
rate is, that is the, your gamma dot
Hmm.
approaches, kind of closer to zero. And what is that viscosity called? Viscosity at that point.
No, not able to recall.
Okay. So it is actually called as zero shear viscosity.
Your shear
Actually,
is
at very low shear rates, you will have, kind of a Newtonian kind of a behavior. That is, a constant viscosity will be there.
yes.
Okay, for very low shear rates, and this shear, viscosity, corresponding viscosity is called as zero shear viscosity.
Yeah,
Okay,
and that is the same thing we call it non-thixotropic behavior.
okay.
Yes.
Okay. So okay, next is question number 6. For yield stress fluids having stresses up to the yield stress. Okay,
Mm-hmm.
from say for example from very low stress to up to yield stress.
Mm-hmm.
Identify the type of flow for strain rate closer to zero. What will be the type of flow for a yield stress fluid
Mm-hmm.
when the strain rate is closer to zero and the stresses are in the range of, some lower stress to up to yield stress? What will be the type of flow?
Stress of the yield stress.
So
Maybe it should be Newtonian flow.
will it be Newtonian flow?
Yes.
Really?
Yes.
Let me give you one more clue. Just focus on the term yield stress fluid,
Yield stress fluid. Okay.
and the stresses are either less than or equal to the yield stress, or just close by to the yield stress.
Mm-hmm. Yield stress fluid means it gives the negative impact. This means yield stress fluid. It is term. So it says that it should be non-Newtonian fluid. Is it so?
Shall I tell the answer?
Yes.
It's actually no flow.
Oh, okay.
It's generally yield stress fluid. So
Yeah.
if you just look into the equation, so this is the
Mm-hmm.
Herschel-Buckley model. So
Mm-hmm.
this is mainly for your yield stress fluids. So if you just look into the equation, it says
Mm-hmm.
that your stress is equal to yield stress plus K into gamma dot power n. And when your uh, stresses are up to yield stress, till the yield stress, it will not flow at all. Once it crosses that yield stress only, once it starts
Mm-hmm.
yielding only, it can flow. Till then,
Okay.
your material cannot flow at all.
Right. Right. Right.
Okay, and when it has stresses greater than your yield stress, for a
Mm.
constant strain rate, it will have a steady flow.
Right.
Okay,
Right.
so that is why I told just stress upon the term yield stress fluids.
Mm.
Okay, yield stress fluids, it cannot flow. That too, the strain rate is zero also. Okay. Okay. Now let's go on to question number 7. According to general definition of normal stress differences, for a viscoelastic fluid, N1 and N2 denotes normal stress difference in dash and dash. Each of N1 and N2 denotes some direction of stress difference. So, which will which of those denote what kind of direction of stress, normal stress difference?
No idea.
Yeah, of course, if you don't go through the lectures, it will be difficult.
Yes. Actually, I have not gone through the lecture.
Yeah. Okay. So actually, N1 denotes the normal stress difference in the direction of flow, and your N2 denotes the normal stress difference in the direction of shear.
Yeah.
Okay.
Okay.
So this is what is the lecture content where it discusses. So here your N1 and N2, as I said, in viscoelastic fluid, even though there is a simple shear flow, due to these entanglements and relaxations involved and reptations processes involved, there is a normal. One second, someone has joined. So because of the these material behavior of entanglements and relaxation processes and all, even in simple shear flow, you will have a normal component of a deviatoric stress. Okay.
Okay.
And this leads to a normal stress difference, and this normal stress difference doesn't go to zero, and you will have a value for that. So that is what is given here in the general definition. And one of them, this N1, it denotes the direction of flow in which the fluid is flowing. The other one is the direction of shear. The shear travels in the y direction. For example, in this case, if you take x and y, x is the horizontal and y is the vertical direction. So in this direction, in your x direction, your N1 component comes in, and in your y direction your N2 component comes in. That is your N2's normal stress difference. Okay, when you go through the lecture you will understand better. Okay, now the
Yeah. Got it.
next
Yes.
question. The macromolecular scale reason behind the development of normal stress difference in a viscoelastic fluid under shear is due to equilibrium dash like macromolecules are dash that leads to tendency of dash. So under equilibrium, what kind of conformation or structure it will have, and under shear what happens to the macromolecules and how the conformation changes, and what does it lead to for this normal stress difference to come into a significant picture. I already gave some clues.
Uh, Actually, difficult to answer once you are not through with your this
Okay,
session.
okay.
Yeah.
Yeah, okay, let me give you the answer. So
Yes.
what happens under equilibrium condition, you will have a coil-like structure for a viscoelastic fluid. And
Okay.
when it is sheared, the coil-like structure gets stretched. And once it is stretched, obviously, the material, it starts having a tendency. Can you just mute yourself?
Yes.
Yeah, because there are a lot of echo. Just mute yourself.
Oh, okay.
Yeah. So what happens is that once it is stretched due to the shear applied, there is a tendency of the macromolecule to recover back also. And this tendency of recovering back, it creates normal forces, and that leads to the normal stress difference in case of macromolecule, even for a simple shear flow. Okay. So the next question. Identify the different techniques of rheology based on application of pressure from the below. So, which of the rheometric techniques or viscometric techniques uses pressure? Extensional rheometer, U-tube viscometer, rotational rheometer, capillary rheometer. Which of these uses pressure? I think one was already discussed earlier. You can unmute and
You can
speak.
unmute. Yeah,
Unmute and speak
like
now.
rotational rheometer always again we use for low viscosity.
No, I am
No,
asking.
I am.
No, actually, when I speak, can you just mute? Yeah. See, I am asking which of these rheometer uses application of pressure on the sample for the flow to happen. Is it extensional rheometer or U-tube viscometer, or is it rotational rheometer, or is it capillary rheometer? The sample has to move, and for that movement you apply a pressure. Which of these rheometer uses pressure, basically a pressure difference or pressure drop for the flow to happen for estimation of different properties? Which of these rheometric or viscometric technique uses?
For application of pressure, normally we use U-tube viscometer.
Okay, that is right. What else? Is there anything else where pressure is used among these?
U-tube is for sure confirmed.
Okay,
Maybe uh, extensional rheometer.
is it extensional rheometer? You have to justify why and how.
So U-tube, I'm very sure because from one side you just apply pressure and then it will raise on another side.
Yes, that is right.
Yes. Uh,
There is one more thing among these where you apply pressure.
maybe we do not apply on capillary rheometer, but there is capillary rheometer works on pressure techniques. That I know. But whether we are
Yes,
applying or not, because it is generic,
yes,
because the
yes,
pressure is on the surface.
yes. So the second one, as you said, it is a capillary rheometer. So
Yes.
capillary rheometer also, there is a requirement for pressure.
Yes,
Okay, or
that's right.
pressure difference basically.
Yes.
Okay, for the
Yes. Yes.
flow, and then your YouTube viscometers. Okay, these two are
Yes.
the rheometric techniques among the
Yes.
given where no
Perfect.
pressure is required. Okay, okay. Question number 10. Consider a polymer liquid system where the partition coefficient for a solute is KPI, which is the partition coefficient, is very much less than 1. Under this condition, dash process occurs. So there is a polymer and liquid system and there is some solute. Okay, and this solute has a partition coefficient of KPI very much less than 1. So under this condition, which process occur? Whether it is an absorption process that is going to occur into the polymer, or it is a leaching process that is going to happen into the liquid, from polymer to liquid.
Uh, Polymer liquid system where the partition coefficient is less than one. That means there should be absorption.
Is it absorption?
Yes.
I have mentioned KPI.
Okay. Partition coefficient for solute is less than 1. Okay. That means leaching?
It is leaching.
Yes.
See, when you look into the formula of KPI, it is, since the subscript is Pi, so it is concentration of the solute in the polymer to concentration of the solute in the liquid system, which is given by Ci. Okay, so Cp by Ci. So if KPI should be very much less than 1, then Ci should be high, whereas Cp should be very low. Right? So obviously the material is much more in the liquid phase. That means it's it has a tendency towards the liquid phase, so leaching happens. Okay. Okay, now the next question is, uptake of a solute as a function of time in a polymer film sample is given by mt by m infinity is equal to K absorption T into T power n, where T is a time. Okay. The type of diffusion where absorption is a linear function of time is called. So there is a relation of absorption. So mt by m infinity gives the absorption. Okay, mt is at point, at any instant of time t. M infinity is at the infinite time or the maximum, absorption. Okay, and k is some constant. So
No idea.
in what type of diffusion there is a linear relationship with time. So the given is a power law kind of a equation. So in order to have a linear relation, the n value should be equal to 1. So what type of diffusion happens when it is a power law, when n is equal to 1? It is actually case 2 diffusion. That is, it is a movement of front between glass and rubbery polymer. So this there was a discussion in the previous week on this dissolution of polymers, especially for sustainability, right? Sustainability aspect, where you use a solvent and it slowly starts uh, dissolving into the polymer. So it happens like in the front line. For example, this is the the square, the rectangle is your polymer and here are the solvents. So it starts diffusing slowly in, and first this portion becomes rubbery and then followed by, with time, the slowly the glassy portion also starts getting rubbery. So this type of, the movement is kind of a, so the front one, it gets transitioned first, followed by the entire film cross section. So this is the case 2 type of diffusion, where the absorption is directly proportional to time and it is a linear function of time. Okay, so when you go through the lecture, you will be able to really get into that. Okay?
Yes, sure.
Yeah. Now the next question is, identify the correct relationship for swelling ratio based on volume and polymer fraction. So is it A, swelling ratio into polymer fraction is equal to 1, or is it B, swelling ratio divided by polymer fraction is equal to 1, or is it C, swelling ratio minus polymer fraction, that is volumetric polymer fraction is equal to 1, or is it D, swelling ratio plus polymer fraction is equal to 1? Which one of these? Can you guess what is the swelling ratio?
Swelling ratio based on volume and polymer fraction.
So as we discussed in the recap, obviously the cross-linked polymers, it will not dissolve but it will swell. Correct?
Yes.
So upon swelling, there will be a volume change.
Yes, it will increase.
Yes. Now this swelling ratio, I am asking for a swelling ratio based on volume. That is, initially there will be a volume of polymer. Then after swelling, there will be another volume of polymer.
Right.
And also the polymer fraction before and after swelling will be different. Right? Initially it is only the polymer. Whereas once it swells, you will have polymer and solvent.
Yes. That's right.
So what is the relationship between both?
It should be D.
Is it D?
Yes.
Okay. You want to have a second thought?
C. Swelling ratio
Okay.
based on polymer fraction. Polymer fraction. Swelling ratio will be volume. Swelling ratio means V2 upon V1. Lateral volume upon initial volume. And then polymer fraction will be low because polymer upon polymer plus solute, polymer ratio will be low. So actually, calculation it is revolving on mind. It is. I think it should be D. Both ratio because one is reducing, another is increasing. So ratio should remain to one constant.
The thought process of uh, identifying what is the spilling ratio and what is the volume fraction of polymer and all is right, but your answer is
Uh,
wrong. It is actually
okay.
option A. So
Uh,
swelling ratio, volumetric swelling ratio into polymer volume fraction multiplied by
okay.
volume polymer volume fraction is 1, which is nothing but it
Uh,
says that polymer
yes,
volume
yes, yes.
fraction is
Multiplication.
inversely proportional to your swelling ratio.
Got
Okay.
it. Yes, it should be multiplied because it is
Yes.
ratio. Yes, it should multiply, not the plus. Yes.
Yeah.
Got it. Got it. Okay.
Okay. Yeah.
Yes.
Now let's go on to question number 13. Swelling leads to dash of segments and dash in entropy. What happens when a cross-linked polymer swells upon uptake of solvent? What happens to the segments? And once the segments a change in segment happens, what happens to the entropy?
So, in my view, there when swelling leads to separation of segments and reduction in entropy.
Okay, partly you're right. Is it separation of just separation of segments? What much more in a technical way you will say. What really
Uh,
happens, mechanically, technically.
maybe we can use a term like separation leads to low energy of segments or low bonding of
No,
segments.
no, no, no. Separation of segments, but
Yes.
in a different term.
Uh,
Think of the synonyms of separation. What happens? How does this separation happens? In case of polymer chain, a particular chain is there.
yes.
So imagine 2 points and two crossing points are there.
Uh,
So what happens to
break,
the
breaking
chain
of
between those points? The chain
breaking
between
of
two. Huh?
breaking
No.
breakdown
If
breaking.
it breaks, obviously the system will not swell, right?
Yes.
It will start dissolving.
Yes. That's right. So separation or maybe elongation.
Much more in a precise way.
Yes, please.
It is actually stretching. The points
Stretching.
get
Yes.
stretched, right?
Yes. Elongation. Elongation. Same word I use is
Yes.
elongation.
Yeah. So it actually
Okay.
stretches, and because of the
Yes.
stretching, the number of conformations in the stretch state, it can take becomes less. So since that
Yes.
capability of taking different conformation reduces upon stretching, the entropy decreases. Okay. Yeah.
Yes.
Okay. So that is what is given in this also.
Yes.
Okay. So this is what is the osmotic pressure change and the network elasticity relationship, and this is based on your and the network elasticity can be estimated based on your ideal chain model. Okay, where the swelling leads to stretching of segments and decrease in entropy. Fine. Now let's go to the next question. Identify if the statement is true or false. As the interaction parameter chi becomes more negative, the swelling ratio decreases. Is it true or false? I think it may be very difficult for you to really think in this aspect until you have gone to the
No.
Flory-Renner equation.
Interaction parameter becomes more negative. More negative means the swelling ratio. Interaction parameter negative है, that means swelling should be swelling ratio decreases. No, it should be false. अगर वो interaction parameter मेरा down होगा तो swelling will be more. Interaction forces less होंगी तो swelling should be more. I think it should be false.
Okay, you are right. Okay, just mute yourself. So, can you just mute? Yeah. So, though you didn't go through the lecture, but logically you have said, yes, it is false. As you said, when chi is more negative, in the interactions between the solvent and the polymer is more favorable. So more and more, chi being more negative implies higher and higher swelling ratio, and this is based on the Flory-Renner equation. You can see that this chi, so it is minus chi. So it becomes minus of minus some value, it becomes plus, and obviously your swelling ratio will start increasing. Okay, whereas it is inversely proportional to your cross-link density. Okay, yeah,
Yes. Yes.
because as your cross-link density it increases, the swelling becomes less. Okay, yeah. Sorry, I think I have already told the answer for this. According to the solution of Maxwell model based on viscosity for an oscillatory strain rate, the first term corresponds to, oh sorry, I haven't told the answer. The first term corresponds to, so as I have I discussed in the recap. Okay, this is the solution. The below is the solution where tau of t is equal to gamma naught dot into eta by 1 plus omega square lambda square sine omega t minus eta omega lambda by 1 plus omega square lambda square cos omega t. This is the solution for a sinusoidal input of strain rate for a Maxwell model. So I think I have told the answer. The answer is here. Okay, it is actually the first term corresponds to the viscous contribution to the stress as it is in phase with strain rate. And the second term obviously is the elastic contribution. So do you remember something very similar relationship? So in mechanical behavior, you saw that G prime, your storage modulus is your elastic contribution and your loss modulus is your viscous contribution. Whereas when it comes to strain rate as input, your eta prime is your viscous contribution, whereas your eta double prime is your elastic contribution. A similar relationship happened in electrical behavior also. Do you remember what is that relation?
Not really.
Okay, so it is the relationship between your dielectric behavior and your dielectric permittivity and your conductivity. So in case of your dielectric permittivity, you will have your epsilon prime, okay, which is a storage behavior. The charge gets stored, whereas your epsilon double prime, it shows that there's a flow of electrons or it is a dissipative behavior. Whereas in conductivity, your sigma prime is your dissipative behavior where there is a conductivity or the flow of electrons, and sigma double prime, it implies storage behavior of charges. Okay, so you could see analogies between your mechanical response and your electrical response. So you have to just start connecting things so that you will be able to understand and remember better and learn better. Okay, there are analogies between, very similar analogies, right? Like here you have between your viscosity and your modulus. There it is between your electrical permittivity, dielectric permittivity, and your electrical conductivity. Okay.
Sure.
Yeah. Okay.
Yeah. Okay.
So this is for the practice assignment. So there were some doubts that were raised in the forum. I'll just try answering some of those. So one question was posted by Uday Kumar. So he has asked, mixing of polymer with another polymer is called polymer blend, whereas mixing of individual materials is called composite. So he is asking, if it is such a way, then can we call polymer blend as a composite? So what is your thought process on this?
Uh, what it says, mixing of polymer and another polymer is called polymer blend. Okay, mixing of individual material is called composite. Okay, such way that we can say all polymers blend are composite. No, I don't think so. Polymer blend is something different and composite is something different. Individual materials, when you are mixing and there is no such uniformity is called, then we call it composite.
It's not about uniformity, but it
Yes.
is more with the material system. So in case of polymer blend, it is different. Two
Yes.
different polymers are brought into contact. Okay, and they are
Mhm.
blended or mixed. And even in polymer blends, there's a different terminology when it comes to two immiscible polymers which are
Mhm.
blended, using some compatibilizers, and that is
Mhm.
classified as polymer alloys.
Mhm.
Whereas when you take into polymer composites, uh, it is mixing of polymer with completely different class of materials in most of the cases, like your glass fibers or carbon fibers, like your carbon nanotube, or graphene, etc. So it is a different class of materials, that are getting mixed. Of course, when when you had gone through the sustainability class, even the recycled polymers can be reinforced into the polymers to create composites. That is of course there, but still, it's better to avoid confusions and define them as per their name that has been generally defined. That is what is the because the systems are different. Okay, I think, hope you got the point. Okay.
Yes, yes, I got the point.
Yeah,
Yes.
yeah. And then one more question was that someone had asked in the 80th lecture, uh, the video, the, there is an explanation with the plot, but the plot is not visible. Okay, so this was on the mixing in different flows, where the professor, he was explaining on the shear flow, where the points get separated linearly with time, and in case of extensional flow, the materials get separated. The separation between the points is exponential with time. So he was explaining on the 2 points. So now actually, the objective of the explanation was that, so in case of, consider 2 points, see the vertically placed 2 points. So in case of shear flow, so this due to application of shear, this particle starts moving, and the flow is the flow, sorry, the shear direction is vertical. So obviously, the once the flow starts to happen, this particle will start moving, and this particle will also start moving, whereas the separation points, it will start going like this, slowly it will go linearly. Whereas in case of extensional flow, what happens is that the materials are pulled apart. So they, if you consider these 2 points again, what happens is that this point is pulled apart, and this point is also pulled apart. And during this extensional process, there is also a reduction in the thickness. So these two effects together, it makes the flow to be exponential. That is, the points get separated. The separation effect is exponential in numbers. That is what he was trying to explain. Maybe the since the video did not cover the plots which the professor was drawing, that is what he was asking. I think this was posted by Shivakumar. Hope he gets the clarification based on this. Okay, these were the doubts that were asked. So, and that's it for the session.
Thank you.
Yeah, any other doubts you have?
No, thanks.
Okay, fine.
Thank you.
Okay,
Bye.
fine then. Have a great evening. Thank you.